Welcome to my talk. This is Bloat in PostgreSQL, a taxonomy. My name is Peter Gagan. I work for Cont. I'm a PostgreSQL major contributor and committer. So talking about bloat today, something that much has been said about, and I'm taking a little bit of a different take today. I've got a strong interest in this, particularly from an indexing point of view. Some of that will come through today, perhaps. Also, there are some citations that you might want to look at in your own time. At the bottom here, there's the URL. I think you can see it. I'm going to upload my slides there later on, and there might also be the facility to do that as part of the conference. I think there's a wiki page or something. I'll make a point of doing that as well. So I think it's useful to do this because you might find that you want to revisit the slides and to reinforce what I'm talking about. It's somewhat intended that you might want to do that. So pointing that out now. Also, there's going to be opportunity to ask lots of questions. Otherwise, why not just watch it on YouTube? I assume that's what makes it worth showing up for. So, all right. So, ordinarily, people talking about vacuum bloat will tend to take a top-down approach. That is, they'll talk about here is vacuum, here's what it does, and this is a valid approach, maybe the best approach. What I'm doing today is kind of the opposite. I'm talking about it bottom up. So I think this is useful because it might fill in the gaps, so to speak. It might improve your intuitions about how vacuum forms. I can't make no promises of that, but I think there's a good chance. Okay, so we're going to talk about structure, definitions, things like that first of all. So I'm going from the page level up. So I guess the taxonomy, to cut to the chase, is you have page bloat in indexes, you have page bloat in tables, and then the next level up you have bloat in logical structures, relations, and perhaps even at the top level you have an even broader idea of having to, when you're doing freezing, advancing the point that is considered to have been frozen before the database level transaction ID. So that's the way we're doing it today. So MVCC, I'm sure most of you know this, or all of you know this, is about versioning, having multiple versions. Postgres, this means having multiple versions in the same place as you have them. You have the most recent authoritative versions. This may or may not. You may or may not also have a version within indexes, depending on whether or not the hot optimization is effective. So let's talk about the heap structure itself. It's optimized for sequential access, but also accessed by index scans. Records are identifiable by TIDs. You can actually, perhaps some of you know, you can actually select star from table where ctid equals something like that, and it'll show you the records that way. This is the same way that index scans work. You're just specifying the TID up front. Sometimes this can be useful. So I think what's interesting about this is it's sometimes called a physiological identifier. What does that mean? Well, it means it's a hybrid between physical and logical. Some of you will be familiar with other systems such as SQL Server or MySQL that have clustered indexes. That is, the secondary indexes, rather than referring to a TID, refer to primary key value and are basically dictionary type structures from secondary index keys to the primary keys. So you have to do a secondary descent of the main clustered index that way. In fact, the TID itself is not strictly physical. It's a hybrid between physical and logical. The first component is the block number. That is a simple block offset in terms of A to K pages or blocks. Second, though, is logical. The item pointer number is, you could think of it even perhaps as being the primary key within a page. You could perhaps put it that way. That's maybe a bit of a stretch. So let's make it more concrete. This is an image from a tool of mine. It's an open source tool. It's called pgHexEdit. This particular image is of the pgindex catalog relation. It could be a user table just as easily, though. How well can you see that? Is that reasonably clear? Hopefully you can make the main, you can get the main outline of it. So this is in pristine order. What does that mean? Well, here we see these are item pointers, these blue things. These are of fixed size. They're 4 bytes apiece. This one points, there's this area here, which is sometimes called the hole in the middle of a page, which is quite small here because nothing else will fit. So the last item here points to the first item here. Ordinarily, we add items from item pointers from the start here and tuples from the end, which would be down here somewhere. And they meet each other, maybe not in the middle. Depends on how wide the tuples are. Could be in the middle, could be closer to the top, as we see here, because these are relatively wide tuples. Point is, there's an indirection at the page level. The page is perhaps its own little universe. If we were to rearrange things within the page, indexes wouldn't need to be updated. They'd be none the wiser because, of course, they have that logical component, the second part of the TID. Index lookups. So indexes are obviously concerned with accessing data through forming lookups. That's clearly what they're all about. So there is a question, though, of because of the index structure, where a value is allowed to go. It's not like with table where you can pretty well put a new thing wherever happens to be convenient. Owing to how indexes work, you are pretty well constrained in where they can go. I'll show you something to illustrate that in a moment. However, the page has much more in common with the heap page than you might think. It also has a sort of physiologicalness to it, which means that you can, because you need to, on a B-tree page, things need to go at a specific point. The indirection is very helpful for that because you only need to shift around the item pointers, the blue things at the top. So suppose you have to put something right in the middle of the page. You might actually physically put the tuple, where free space begins in the tuple area, and then you'd have to shift some of the array to make room for a new item pointer, but it would be, so the indirection there again is helpful. You have this layer of indirection which makes all of these things that are essential so much easier. Here's an image of a B-tree structure. This is a real Postgres B-tree, in fact, generated with some custom graph tool visualization. You would need 10 more projectors, in fact, if you really wanted to display this. And this is a fairly small one as well. So, there's a tremendous fan out here. It doesn't really look like a tree structure at all. It's like a bush. And in fact, if you had a realistic sized one, it would just look like a straight line, like a horizontal line, because there's you have a logarithmic rate of increase in the number of levels. So it's not like a tree at all. What's also interesting here from the point of view of discussion of bloat is here you see these values restrict what. So suppose this was integers. Only so many integers are supposed to go on this particular page. When you're inserting any given integer value, there is always one particular page that it's supposed to go on by virtue of the downlinks, the branch pages, saying that's where it's supposed to go. Sometimes there's negative and positive and negative infinity involved, but basically there's always a definite place where every value belongs. So the implication is, of course, the implications for bloat here are considerable. So here we see another similar image. This is of actually a catalog index, and as I said, you can't see the page header as you did before. It's because I had to scroll down a little bit more. It's sort of up there or something, but these are all the same. The page header will be the same if you could see it, and there's an awful lot of commonality there, even though at a higher level these are very different sorts of structures. I'm also going to mention, in the context of, starting from the bottom, without going into too much detail, this question of transaction status data. There are things like commit status information. This is in PG exact directory of your Postgres data directory. Bitmaps typically that store transaction status information that must eventually be truncated by freezing. This is mentioned. This is not really the emphasis of the talk, but it's mentioned for completeness. This is never something that opportunistic garbage collection can deal with. You always have to be formally running vacuum here. It is also page-based, though. There are in fact 8K blocks involved here also. I also should mention free space map, visibility map. These are also maintained by vacuum, and again, a lot of similarity between these items and the aforementioned SLRU stuff. These are maintained by vacuum, and it isn't something I'm going to go into too much detail on. With that, I will take questions if anyone has any. This is a point in which one of the points I'm going to take questions if anyone has any. Okay. I guess not, I'll continue then. So here's the actual bottom-up take. We're going to talk about vacuum hot and the relationship between index and table bloat. This is an image of a generic animal cell. It's kind of a visual metaphor, something I have a weakness for. Basically, the idea I'm suggesting here is pages can sort of be thought of as being a little bit like cells, because that was a generic representation of a cell. You remember from high school biology, perhaps. There's an awful lot of commonality between different types of cells within an organism, even though the actual purpose is fairly disparate. Organs, whatever it might be, are comprised of cells, and yet these are all very different things, and yet you can do an analysis of just the cell, and you can reason about that almost as an independent thing. So I think that the page model is quite a bit like that. That is, I think, something that I think that it's a little bit of a contrived metaphor, but I think it sort of works. In general, with a system like Postgres, we have complicated atomic operations, that is transactions, but these are ultimately comprised of simpler ones, and in particular, atomic operations against pages that are well-logged. We know how to make simple things atomic, and we sort of build our castle of atomicity from these simple little parts. This is a quick couple of quotes from Torvalds. Not necessarily a blanket endorsement of his views, but he points out that there's an evolutionary nature to how Linux has come to be. He also separately has this remark on data structures, which I think is kind of apt. It's often best to focus on the data structures and let the code follow from that. I think it certainly clarifies certain things. I don't want to stay with that for too long. So there's this question of how you deal with complexity. I think if you think about it in those evolutionary terms, maybe that clarifies it. Having the pages as an independent, self-contained thing you reason about, and having that abstraction amongst different access methods and leveraging it to hilt is really important. Okay, so talk about bloat at the page level. You can often directly observe bloat at the page level. Of course, in general, bloat means that things that are on the page are no longer visible, and that may not be directly represented. That may need to be inferred from the transaction status information that's stored on tuples. But often you can directly look at it, say, through a tool like pgHexEdit, because there's some amount of opportunistic cleanup that goes on. There are hints of it. There's also this thing called hint bits, where once a transaction commits, we'll remember that the transaction that affected that tuple committed, and therefore there's no question of whether or not it's committed. We don't have to go to the commit log. We can directly know that it is visible. Also, there's this thing called pruning. Anyone here go to the Grant McAllister Hot Talk? I guess some of you must have. So he undoubtedly talked about pruning. Pruning is something that's very important in the context of hot, but I think there's a danger in thinking that that's just what it's about. It's broader than that. Pruning is something that vacuum also performs. So here we see these red item pointers. These are LP dead. And you can actually see, if you look very carefully, which you probably actually can't see, there's some stuff here, even though there's no annotation, you can tell that there used to be something there, because the way it works at a low level, that doesn't get overridden because there's no reason to. These are kind of like ghost bytes, perhaps you could say. These used to be index tuples, or actually, I think heap tuples, but they are no longer, because these no longer indicate that there's something there. These are dead. This happens after pruning, which might be opportunistic. It might be performed by vacuum if vacuum doesn't get the opportunity to finish. Vacuum is, by its nature, of course, concerned with bulk garbage collection. Auto vacuum is typically what runs vacuum, triggered by fairly simplistic thresholds. It shouldn't be confused with vacuum full, which is a far more aggressive operation, which essentially rebuilds everything from scratch. It has a very aggressive lock level, and it really is quite different. So I'm just pointing that out. So the first phase of a vacuum, in fact, is pruning. So really, it's almost exactly the same as opportunistic pruning. I'm going to talk more about that now. There's a question of what are you depending on in your workload. I think you'll tend to depend on all of these things. There's more than even one type of opportunistic garbage collection, and then of course there's vacuum. I think it's hard to predict. It's hard to understand even what degree you rely on each. But there's a good chance you are relying to a significant degree on opportunistic garbage collection without even knowing it. I mentioned also vacuum can sometimes, if it so chooses, skip stuff because it can't immediately acquire the right type of lock that it needs on a page, not to be confused with locks that are managed by the lock manager. So it is itself perhaps a little opportunistic, or at least can be. Processing order vacuum. This is what vacuum does. These are the steps at a high level. So we visit the heap. We perform pruning. As I said, the same as opportunistic pruning. We mark the item pointers as dead because the indexes that we most likely have on the table will require that the TID that they have stored will continue to be valid for as long as those entries exist. We need to do pruning first of all, which is actually where the bulk of space is reclaimed in the heap. only then, having gathered the list of things to go kill in the indexes, can we go kill them in the indexes, at which point finally we do a second pass over the heap to mark the item pointers as unused. Now there's a couple of things that are interesting. Probably a lot of you have like a rough idea of this stuff already, but I think there's a couple of things that are particularly worth noting here that maybe could be missed. You can think of the processing order as being dictated by the same requirements that we see at the page level for opportunistic stuff. So in other words, we cannot just go ahead and kill everything up front when we do our first pass of the heap, because then you'd have index entries that pointed to nothing, or worse still, pointed to some other thing, which would give you wrong answers to queries. That's not going to fly. That's a hard requirement, obviously. Now, there is something about, so we sometimes say hot pruning, but it's not really hot pruning at all. It's really just pruning. So hot, as some of you would have heard, is this optimization whereby you don't create new versions of things in the index. You instead just, within the same heap page, create a forwarding link to the extant current version that you're updating. And from there, you get away with needing to put new stuff in the index, because provided the values are the same, you didn't update any indexed values, index columns, I should say. From there, you know that you can you can get away with not doing that. You can simply have index scans find the original root within a single heap page, and from there find the version that's visible to them, that's current to them, and you don't have to update the indexes. That's primarily why hot is valuable, because you don't have to do all that work in the indexes. You don't have to dirty the index page, which has I/O cost. You don't have to do any of that. But also, as you may have heard from Grant, you can also do pruning. I'm not calling it hot pruning, where you can, the stuff that is between the root pointer and the most current, you can just sort of cut that away immediately. This is important. This is particularly compelling because you can imagine, and certainly even observe, scenarios where the steady state is that you're continually updating this one heap page as you update continually, and there's never any, you never have to fail to contain it to that one page. So there's a cycle of never exceeding a certain overhead. You don't fail to reclaim any space at any point potentially, and that's great. But there's also something not to be missed is pruning. Also, basically, even if you don't have hot updates, even if you are actually updating the indexed columns, you still can prune away the root and make it LP dead. So you have that 4 bytes left over. The item pointer must remain there until vacuum can run, and in particular until the second phase of vacuum can run and mark it as reclaimable. But you've still, if you do the accounting, reclaim most of the space, even though you're not really getting the full advantage of hot. Just to do the math, I said 4 bytes for the item pointer. It's not nothing, but then you have the standard page header is the standard tuple header is 24 bytes. So the real minimum size of tuple you can have is 30 bytes, and it's probably more like 40, 50, 60 or something like that. So 4 bytes is relatively small potatoes a lot of the time. So even though you're not getting the full benefit of hot, you don't have that nice property of being able to continually reuse space without any leaking, so to speak, until you have a vacuum. You do get a significant benefit there, even still. Okay. There's also another opportunistic technique for garbage collection for various index access methods, in particular B-tree. This is much less well known about. you don't have to know about it. You just get it for free, largely. There's no question of, there's much less of a question of arranging to get it by being clever about what indexes you define and don't define, as there might be with hot. So this is a little obscure, but worth noting. So within B-tree, there's this LP dead thing. And basically, index scans can say, oh, this isn't visible to any possible transaction or snapshot. I can go ahead and mark this as dead to everyone, and then immediately no one else will have to follow. They'll simply see that it's dead, and they won't do anything with it. They'll skip over it without having to go to the heap. And then even later, they'll be able to, when you have a page splitter, or when it looks like you have to, when you're at the verge of requiring one, you can then say, oh, you know what, I can actually just reuse the space, and I can forestall the page split, which is important because you really don't want to have too many page splits because of a short-term accumulation of stuff in an index. That can be very difficult to claw back from without a full reindex. And of course, index bloat is perhaps a lot more harmful because it's not obvious that it can be reversed if you allow it to get bad enough. At least with heap bloat, you can imagine clawing back eventually when vacuum does run, but that is a big difference between index bloat and heap bloat. And this question of the relationship also, I'm really just reinforcing what I've said here. There's this the heap tit has to be stable, and that restricts you. So the more opportunistic pruning you get, you tend to get the page has more and more and more item pointers because you can't reuse that. So that eventually forces you, even if you forget about freezing or any of that stuff, you might have to do a vacuum just because eventually you'll have too many of those dead item pointers that you need to reclaim. So that might be the forcing function for vacuum and not anything else. But you're still getting a decent benefit before then with the opportunistic pruning, even assuming you don't have hot updates at all. With that, I will take questions. Yes?
Just a question. So what you're saying is when the item pointers are marked dead, you actually are allowed to reuse that space. You just can't reuse the item pointer until it's been cleared.
Yes. So we're talking well, that's... Yeah. You're glad you came then.
That's why we're
Yes,
here.
that's right. So yeah, I think a lot of people didn't realize that. Probably most of the space is being reclaimed by pruning. Yeah, you have to do the second pass with vacuum, but if you were trying to think about it in terms of space reclamation, that isn't really reclaiming all that much space. The pruning is where you're getting most of the stuff back, right? Anyone else? Any other questions? It can be. It can be. It depends on an awful lot of things. The access patterns. When I say opportunistic, it's also so queries that are running they'll observe. Oh, I have to do an update, but I can't fit it on the page. So I'll try to see if I can get this low-level lock on the heap page in order to do a prune just of that one page. So it might be that something could hinder that if there's a lot of contention. But in general, this will tend to happen quite a bit within backends that are executing your queries themselves, both for the heap, but also, as I mentioned, for actually, if you're talking about the index one, that's a bit different because this is any old index scan will tend to set those bits as dead. So there's less of a question of being able to acquire the appropriate lock. There really isn't a lock required. It's only a single kind of hint bit, which is a difference. Anything else on that? Yes. I'm sorry. Yes. Well, no, and that's kind of the thing is you have to have known that the index entry. So there's no. One thing that you could imagine happening but doesn't happen is that you go to prune the heap page and then you go to all the indexes and you go delete that stuff and then you come back and then you get rid of everything. But that only happens at the relation level. It doesn't happen at the page level. It's been argued that it ought to. In fact, I'll get to that. But it's very clear, though, that you need to have an item pointer if there's an index entry, and it needs to be substantively the same as always. Otherwise, you have something pointing to the wrong thing and disaster. So does that make sense? Okay. Yep. Yes.
You mentioned a number of different behaviors and cases that happen during query execution and vacuum and things like that.
Right.
Are there metrics about any of these things, or ways of tracing them to see, how many times am I running into a case where, where we hit something in the index and we needed to look it up anything, but it was already dead?
No, because, well, there are of course the pgstat.io and pgstat tables that do summarize things at a higher level than that. The overhead, given our current model for these sorts of statistics, would be prohibitive. One can imagine a world, though, in which we've managed to decrease that overhead and thus can afford to store that much more. No, there's no easy way of getting instrumentation on that, unfortunately. Anyone else? Okay. I'll get on with it then. So I'm going to talk a bit about the priorities of vacuum. Vacuum, of course, is something that needs to consider what you as a user care about and what you as a user are presumed to care less about. Vacuum has its own set of priorities. So there's often a question asked about, why is it that this or that relation has a certain storage overhead? Intuitively, it seems like it ought to be quite a lot less than that, given the nature of the churn I know that this table has had, that kind of thing. And that's a very natural question to ask, it seems. A lot of people seem to end up there with it. And the fact is that space reclamation is not the number one priority. The number one priority is query response time and making sure that the locks required in order for vacuum to run are not too aggressive, and for the same reason, that is, so that your queries will not be adversely affected. So there is also, with the way vacuum works, in contrast with other systems, in particular Oracle, is, as I said at the start, the structure that stores old row versions is in fact the same structure that stores the new ones. Long-running transactions can be very, very harmful because they accumulate bloat in that same structure. I've said already, you can imagine reversing that with vacuum for a heap, because a heap doesn't have any constraints or has minimal constraints on what goes where, whereas an index is rather a lot different. There's only one write page for any given possible value. It's not so you want to really avoid index bloat. Again, hot is very important for this. The burden is placed on not on the old snapshot, the old query that's running or has been leaked or something like that. It perhaps would be better if we were able to have that do the extra work of going in, looking in some kind of subsidiary structure such as undo to find the old version that way, rather than accumulating it in the same place. So you really want to look out for long-running transactions as a practical matter. I mean, if you delete something and it's and then you commit your transaction and it's unambiguously deleted, it doesn't mean that it's not still visible to this old thing. So you have to keep it around. That only would occur when it's only possible for it to be not just recently dead, as we say, but fully dead until such time as the oldest transaction that's still, or rather the youngest transaction that still sees it as visible goes away. So again, to emphasize, long-running transactions are potentially very harmful. So it's non-disruptive. Another thing is interesting about vacuuming of B trees is it's actually in physical order. unlike any other sort of access to the B-tree structure. That is, you're accessing it from in sequential order, even though, depending on the exact details, it could be a straight index scan could access it in pretty random order. An index is a tree structure. There's no reason why an index scan could jump around at random, depending on the order in which the pages were initially created, how space was reclaimed, and things like that. But vacuum is able to access the indexes in fully sequential order. There's some trickery around that. So that means that it could be potentially an awful lot faster than just accessing it directly with a full index scan. Of course, you have this sort of eager versus batch dichotomy with space reclamation. You want to be eager if you can be. There are advantages to doing it by batch as well. It seems to be pretty fundamental to how the MVCC model that we have works, that you kind of need to have both at the same time to get acceptable performance. Also, with indexes, only entire pages can be reclaimed, given back to the free space map at once. So if you can have something called there's a specific situation. If you have sparse range deletions with an index where you have, like, say you only have one index tuple left on a page, that is enough to prevent the system from not being able to reclaim the entire page. The system is unable to merge adjacent pages that are almost empty. They have to be fully empty. So there can be certain patterns whereby you tend to get a lot of sparse deletions, and that is something to look out for, perhaps, in certain scenarios. I'm working on this stuff at the moment myself. So. And with that, I will take any questions you might have on that. Okay. Yes, sir?
What about the non-B-tree index space?
So I can't remember which so mostly they do have to be accessed as if it was a full index scan, which is bad because usually that means you could have a lot of random I/O, where you're almost guaranteed not to have that with B-tree. That's a significant advantage for B-tree. Is that what you're asking about, or some other aspect of it?
Yeah, but think about sparse population, particularly of prefect index.
Yep. That would be a GIN index, I suppose.
Yeah.
Yep. So GIN has page deletion, but not of the main entry tree. So the way GIN works is, in short, you have like one main entry tree. Suppose it's to keep it simple, not full text search. Let's say an array of integers, an index on an array of integers, where you can, with the GIN index, there's a containment operator that you can index using a certain op class, GIN op class. Just keep it simple. So your main entry tree is in fact directly storing integers. You're indexing, the type you're indexing is an array of integers, but the main entry tree will just have not an array of integers, but integers. And then it'll have a posting list potentially of TIDs, and then it will potentially, if you have an awful lot of duplicates, which you might well hear, then you can have new B trees that are posting trees that they're like trees that are comprised entirely of TIDs, heap TIDs, as values. So that's how it can deal fairly gracefully with having an enormous number of dupes. Now you do have page deletion engine of these trees. You can delete those pages, but you can't delete the main entry tree pages. It's a question of trade-offs around concurrency. You'd have to impose a cost, perhaps, or it would certainly be more complicated for index scans you'd have to have a protocol that prevented various sorts of races if you wanted to support deletion. B-tree does support deletion, as I said, but it has that restriction. I'm told that that the choice of only deleting entire pages is generally thought to be a good trade-off. From this point of view, I think SQL Server supports merging pages that are not entirely empty, but at some considerable cost. We have this sort of clever way of avoiding lock coupling or latching, where you have to do this when you're descending the tree with your locks. You have to hold one, and then you get the one below it, and then you have to have at least one at a time. We can just avoid all that because I think there's a trade-off there between that and merging. So I believe that's actually probably the right call there. So future work, stuff coming in V11, which is out just a few weeks, and beyond. So this is something you could have easily missed, but I think is well worth being aware of. It didn't get a lot of press, but I think it's a good one. So some of you will be aware that in 9.6, the visibility map was overhauled so that it could represent pages were frozen. And so now it wasn't just possible for Vacuum to skip pages that it knew had no garbage, but could also potentially skip pages that also were completely frozen and thus need to be frozen again. This is very important if you have an append mostly table. Your cold data, you want it to stay cold. You don't want to access this stuff that you've frozen long ago, because you have the metadata to know, that's not necessary. I did that months ago. But there was a bit missing, which we now sort of have, around indexes. There's now the ability to also, at the same time, skip vacuuming indexes when you similarly know that's not necessary or of only marginal value. So there will be cases where you can skip vacuuming indexes more. And again, kind of just complementing the earlier 9.6 major feature around avoiding the need to refreeze having frozen before. I'm working on this bit myself. Yes?
How does it track whether an index needs?
It tracks it. You mean I'm not quite sure what motivates the question. Could you expand?
With the visibility map.
Yes.
So what is the complementary thing that's tracking the index?
So I don't want to recall the details wrong right now. How much for time? I'm okay. Basically, if you have no garbage in the index, you might, in theory, need to go to update the free space map for the index, but you can track whether or not that's likely to be true based on what you did last time. So that's stored in the meta page of the index. So there's a little bit extra accounting around things like, were there any fully empty pages, which is not very likely. Yes, there are workloads where it's extremely likely and important, but on average, it's not that likely that you would be giving too much space back to the free space map owing to that restriction, perhaps, that I mentioned about only being able to reclaim whole pages at once. So does that answer your question adequately? Is that sort of so it's just about observing. Yes, that's true. I mean, it isn't terribly much more, but it could make a big practical difference because, hey, yes, you've saved an enormous amount of work because you don't have to continually scan the table. But if you're doing a vacuum freeze every few days, which you could be if you have enough transaction throughput, it was kind of a shame that you could still have to do the indexes. But now we've somewhat solved that problem in 11. So something to look out for if you have a big table that you freeze periodically that causes you, or continues to cause, rather, pain in production. Okay, so yeah, I'm working on this thing of, I'm adding a bunch of Flask optimizations to the B-tree code in the 11th cycle. That's my plan, at any rate, in order to facilitate opportunistic cleanup of indexes at the same time we do opportunistic cleanup of bloat. So I'm kind of, someone asked a question over here, I think it was you, sir, about doing it at the page level at the same time. There are very tentative plans to do that. My low-level work on B-tree code will perhaps facilitate that. That work is also intended to facilitate work by others, mostly DB people, on something called Z-heap, which is an alternative storage format that puts the bloat somewhere else so that it can be accessed by the old snapshot that needs to access the old stuff, as opposed to imposing a penalty on the system as a whole. So, yeah, we're coming at it from a lot of different angles, all at once. So, yeah, vacuum is a thing that it's for removing all tuples in conclusion. There are very much complementary techniques that are all opportunistic. Vacuum, as I said, is the only thing that'll do truncating of these auxiliary structures concerned with transaction status, information, and such like. The opportunistic stuff, if you don't remember the ordering that I was saying, okay, first of all, it does the pruning. If you think about it just in terms of the page, the index page, the heap page, you can sort of reconstruct, oh, yeah, okay, that's how it works because it has to work. That's that way. That's the only way it could work. The first phase is doing most of the work, so to speak. At least it's freeing most of the space, making it reclaimable. The second pass of the heap is only needed in order to release that last little bit. Pruning will not do that. So as I said earlier, some amount of vacuuming is perhaps inevitable, even without freezing being a consideration, simply because that little bit that's left, that little 4 bytes per tuple, that's the only way you get rid of that. So that's how that works. And I'm done. Unless there's more questions, which I'm very happy to answer. I guess not. Oh. Yes?
Is it common for people to see pretty substantial degradation in query latency during auto vacuum or vacuum operations?
It's certainly possible for that to happen. Often I think the answer is yes, simply. Ideally, it would be possible for vacuum to either run at an off-peak time. That's a very common, simple optimization. Perhaps something to consider if you probably have workloads that are bursty in some reasonably well-understood way. You could potentially do vacuuming at nighttime by a cron job or something to keep it dead simple. There's also settings that control how aggressive vacuum runs when it's running. So there's deliberate waits, at least when auto vacuum runs by default. These are actually very conservative, all too conservative. Ordinarily the problem is that it runs too slowly because it isn't aggressive enough out of a concern for affecting query performance. That's probably the more likely problem. Of course, you have both problems. I think the answer is yes. Is there anything you want me to expand on that?
No, that makes sense.
Yep.
Upgrading to a newer version actually makes it a lot better because my experience is that the biggest latency comes from a lot of dirty data collecting in the kernel buffers. And suddenly,
Right.
independent transactions have to write out all that pending dirty data.
Yes.
And in newer versions, we limit the amount of dirty data by default, so that makes it
Yep.
better.
Yep.
You can tune that down, and then performance also gets.
Yep. It's a bit sad that you could, in the second phase of vacuum, even though you're doing a relatively modest amount of space reclamation at that point, you could still, at the same time, incur dirtying of pages, which, owing to how checkpointing works, it would be almost as bad. So that's kind of a sad possibility that's implied by the fact that there's 2 passes. Anyway, anything else?